We're going to start our look at differential equations with a class called separable equations. First, we define differential equation. It's an equation that contains the derivatives of one or more unknown functions. Those are dependent variables, and we tend to think of those as y, with respect to one or more independent variables, and we often encounter that as x. I have some examples here of differential equations. For instance, dy dx plus 5y equals e to the x is a differential equation. X is the independent variable, y is the unknown function or the dependent variable, and of course we have here Leibniz notation dy dx. Another differential equation example is y double prime minus y prime plus 6y equals 0. This would be referred to as a second order differential equation because it features a second derivative as the highest derivative. dx dt plus dy dt equals 2x plus y is an example of a differential equation that has two unknown functions. One of them is y of t and the other is x of t. These commonly appear in systems of differential equations. All of these examples are called ordinary differential equations because they feature ordinary derivatives, such as dx dt, y prime, dy dx. Partial derivatives are denoted using this curly d thing, and here we have the second partial of u with respect to x, and the curly d is there to indicate that the unknown function that we have, u, has more than one independent variable. Now, I'm not going to spend any more time on that because in this course, we're going to work only with ordinary differential equations. That would be the first types that I just presented to you. A first order separable differential equation, first of all, since it's first order, we know that the highest derivative is the first derivative. Here we see it has the form dy dx equals g of x times h of y. In other words, a product of a function of x with a function of y. To solve a separable equation, we separate variables and integrate. In this case, we're going to separate by dividing both sides by h of y. So let me turn that period into a colon. And we have 1 over h of y times dy is equal to g of x times dx because first derivatives act like fractions and we can quote-unquote clear the fraction. Now this 1 over h of y is still just a function of y, so we can rewrite that. Say we'll call it p of y dy is equal to g of x dx. And then integrate both sides to, well, I don't know. What happens after that depends. A subtle point here is that on the right, we're integrating with respect to x. On the left, we are integrating with respect to y, which might seem a little bit weird, but remember, y is a function of x, so ultimately we're actually integrating both sides with respect to x. We're going to go ahead and jump into our first example. We have a differential equation dy minus the quantity of y minus 1 squared dx equals 0. I'm including a note here that since the y function, the unknown function, dependent variable, is wrapped up inside of a squared exponent of 2. That makes this a nonlinear differential equation. Now I said we would solve this by separating and integrating. And in this case, the separating starts by adding the y minus 1 quantity squared dx to both sides, and then dividing by y minus 1 the quantity squared, which I'm actually going to write down as y minus 1 to the negative 2 dy is equal to dx. On the left-hand side, we're going to integrate using the power rule. Let me go ahead and write down the integral symbols there. Adding 1 to the exponent, dividing by the new exponent is going to give us negative 1 over y minus 1. And on the right-hand side, we integrate 1 dx to get x. I'm going to add a constant to the right-hand side, and you might note we should be writing down plus c on both sides. Well, I'm not going to do that. If I had a constant on the left and a constant on the right, I can just combine them into one constant. Bottom line, we only need one constant of integration. Now it's not going to be too bad in this case to solve for y, so we're going to go ahead and do that by first multiplying both sides by negative 1. I get 1 over y minus 1 is equal to negative x minus c. Well, now c is a constant. We don't usually write down a minus c. So instead of doing that, what I'm going to do is I'm going to say this is equal to c minus x. I've multiplied by a negative 1, but I just changed the meaning of the constant, and so I'm going to go back to the previous step and say, it really was x plus c1. And then I've made a change here, and I'm saying that c is equal to the negative c1 that we had in the previous step. It just makes things look a little bit cleaner. Now on the left-hand side, we have 1 over y minus 1. We're going to find the reciprocal. So we have y minus 1 is equal to 1 over c minus x. Remember, we can't reciprocal individual terms. Adding 1 to both sides is going to give me y equals 1 plus 1 over c minus x. Now this is what's referred to as a one-parameter family of solutions. Each value of c gives rise to a different solution curve, and we could identify a particular solution curve using additional information that we don't currently have in this particular problem. Now I want to go back to the beginning of this. We started out with dy minus the quantity of y minus 1 squared dx is equal to 0. And I want to note that y equals 1 is a solution to the differential equation. If y is equal to 1, then y minus 1 is 0. And if y is equal to 1, then dy is 0, the differential. And then I would have 0 minus 0 equals 0. It solves the differential equation. This is not one of the solutions that we can get by putting in a particular value in place of c. And so it's referred to as a singular solution. It solves the differential equation, but it didn't come from this process. What makes a solution? Any function, here's the Greek letter phi, but any function phi defined on an interval and possessing at least n derivatives that are continuous on an interval, which when substituted into an nth order ordinary differential equation reduces the equation to identity, is said to be a solution of the equation on the interval. Oh my gosh, that was a lot. Here's what it says. If you have an nth order differential equation, a solution, you have to be able to differentiate n times. And this whole reduces the equation to an identity. The bottom line is, if you have a solution and you check your answer and you get a true equation, then the thing you had is a solution. A couple of subtle points. The function has to be defined on an interval, and the derivatives have to be continuous on that interval. And if those hold true, then what we have is a solution to the differential equation.